is going to lead the discussion. He's going to lead the discussion. Yeah, we'll see how it goes. The speaker is a very good speaker in the field. So go ahead.
Okay, today I will introduce a review. The paper name is The Potential of Machine Learning for More Responsible Sourcing of Critical Raw Materials. The author, Richard Logan, he is a head of department in the Helmholtz Institute in Germany, and he used to be a group leader in another institute in Germany. He got a postdoctoral research assistant in United Kingdom and a PhD degree in France. And his research interest is about the multi-source and multi-scale remote sensing integration. And now he's doing some research about combining the machine learning with the remote sensor. And now we're facing a growing demand for mineral resource worldwide. Like the picture show, we could see the gray part and the blue part. The mineral improves to stock and the orals is more and more following the increasing year. But the destructive mining projects always produce a lot of pollutants, and many people have protest for it. And people have a low carbon future consensus today. So it's really essential to develop the new technology for mining to make it more green and efficiency. So the imaging sensors have become a hot point in these sensors. So what can imaging sensors do for mining? The first step it can do is the data collecting. And there are 5 collecting ways. The first is the satellite and the crew aircraft and the uncrewed aircraft and the trees.
It's too bad. Young opted out. I don't know, probably due to the internet connection problem. We'll wait for her to come in. Yang, could you share your screen again?
Okay.
Yeah, go ahead. It's visible now.
And there are 5 collecting way of the imaging sensor. The first is satellite, the second is crew aircraft, and the third is uncrewed aircraft, and the terrestrial and label scale. Like the satellite, the advantage of it is the data from the satellite imaging sensor is open in the internet, and we can get it very easy. And it have a wide range data, almost the whole Earth, and it also offers the time resolution. But we all know it's very expensive to get data from the satellite, and the satellite is so far away from the land, so the information is not so clear for the land, and it can be customized. And how do machine learning make mining responsible? It's mainly about the 3 steps. The first is the data pre-processing. Like the left picture show, the first picture is the RGB imaging, and the second picture is the hyperspectral imaging from the imaging sensors, and the third picture is about the hyperspectral imaging with the topographic correction. And we could see the third picture have a clear boundary and the shape is more clear. And the right picture is about the it's about A method denoising methods. And we could see the 3D wavelet and high res and the fast high date make the hyperspectral imaging more clear, and we could see the information like the lights or the different colors, the black and white, more clear. And the second steps of the machine learning do for mining is the data classification. And the first type is the unsupervised approaches, is also called the clustering. The conventional shadow clustering includes k-means, SSC, ESC, and the deep learning based clustering includes the autoencoders. And the second type is the supervised approaches. The conventional shadow classifiers includes the SVM, random forest, multinomial logistic regression, and so on. And the deep learning based classifiers like the CNN. And the third steps that the machine learning can do for mining is the data fusion. Because we use a single imaging sensors to get data, but now we can get many types imaging sensors like the satellite or the label scope to get different features of samples. So we need to fuse the data to get more detailed information. And the first method is the pixel level fusion. The first step is to accurately fuse the original images like the RGB imaging and the hyperspectral imaging. And the second is calculate a new pixel value through the Saturn strategy. And after we got the new values, we could use the fused data to fit into the classifier to get the classification map and get the value information from this map. And the method of it have two main types. The first is couple non-negative matrix factorization, and the second is IIDF. And the second type of the data fusion is fixture level fusion. The first step is to extract the representative fixtures from the original images. And after we got the fixtures, combine them by using a fusion scheme like a low-rank model or composite kernel. And after that, we use the classifier to get the classification map and get the valuable information. The representative method is the subfirst. And the author also do an experiment to test different classifiers to get the mineral types from the Finland mineral data set. And the data is captured by RGB camera and the hyperspectral immigrate. Like the first picture shows, the RGB imaging. It contains many types minerals, and every type represents one color. And we will use these classifiers to test the accuracy in classifying mineral types. The evaluation index is overall accuracy and average accuracy and the kappa coefficient. Like the right picture show, the second picture is the training samples and the third picture is the testing samples. In fact, I'm confused why it will use a whole black picture to make it as the training samples, because I think the black picture have no information about it. So I'm very curious about how the black picture can make it training the machine learning method. And like the left picture is the classic name, like the clay, dust, water, and dark rocks. And it is the result of the unsupervised approach. We could see from this table, for every classes, like the clay, the HESSC got the highest accuracy, and for the dark rocks, the AE got highest accuracy. And overall, we could see about the OAAA and the kappa index, the AE method got highest accuracy and the ESC method got the lowest accuracy. It means the method based on the deep learning have highest score than normal machine learning. And we could see the right picture, the F, this picture, the F shows a clear boundary and the noise is less than the other picture. And we could see the D picture. It is for the ESC. This method got the lowest score. We could see this picture shows almost green color and it couldn't classify different minerals from the sample. And this is the result of the supervised approaches. From this table, we could see the CNN method got the highest OAAA and the kappa scores, but about different classes scores, the FDSI got the highest clay scores and the highest dark rock scores, and the water, finite, and the feldspar weight scores. So the classes scores and the overall scores is different. And the CN, and it also contains some scores about the fusion data methods. From this table, we could see the subfirst got the highest scores among the fusion methods. But we could see the IIDF have the highest water scores. It got 1% score. And we could see the left picture. Among the supervised approaches, the CNN, the D pictures got clear boundaries and the noise is less than the A and the B picture. And among the fusions, the three-type fusion methods, we could see the subfirst got the clear boundaries and less noise than the E and F pictures. And compare the unsupervised approaches with the supervised approaches, we could see the supervised approaches usually get higher scores than unsupervised. That's because the label of the geology map is complex, and if machine learning make the label automatically, it will make many errors. So the supervised approach will get the higher scores than unsupervised. And the 4 steps that the machine learning can do for the mining is the 3D analysis for point cloud data. The data type usually have 2 types. The first is 2D data, like the raster imagery. It's also called the pixel imagery. And the 3D data is like the picture show. The map is The map is the whole angles from the geology map. So we could see the shoots from every angles. It contain the inner structure and outer structure. And the 3D analysis methods always is mainly two types. The first type is the spatial methods, which make the predictions based on the geometry and the spatial relationships. And the second is the spectral methods, which use the textural fixtures and the point spectra. But now it didn't have a very successful 3D analysis methods of the machine learning because it faced three main challenges. The first is lack of the defined topological structure, and the second is because the point cloud data has a very complex dimensionality. And the third is about the massive parallelization and out-of-court computation and visualization. And the author also give us a list of available resources. It is about the denoising resource, unsupervised learning resource, projection, and correction resource. And we could get the resource opening from the reference. And the challenge of the machine learning in imaging sensor, the first challenge is about the collection of adequate high quality ground truth. And the author offers a solution about it. It is about focusing on the estimating mineral abundance. It will make the label numberized. The second challenge is lack of training and validation data. And the author also gave us a resolution. It is about developing unsupervised, weak supervised, or self-supervised approaches. And also move away from closed data to more open science principles. It will make more teams to create new machine learning methods for the imaging sensors. And the future direction of the imaging sensors with machine learning, it will have three main directions. The first is about developing multi-sensor and multi-score fusion algorithms. And the second is developing advanced classification approaches. And the third is about improving the quality of the input data. So that's all. Thank you.
Okay, thank you for introducing the paper, and I think we could ask some questions and discuss. Actually, from my perspective, it's interesting because this field that they're talking about looks like to me that is all like the image identification to a certain extent. It's interesting because in the mining industry, that might happen to be one of the ideal place for the weak AI to really perform, because it is a location where there will be less people entering the field, because for young people prefer to live in cities and few would like to work in the mining nowadays, at least in China. Similar in a lot of different countries like in Russia or in Europe as well as the United States. And so it is like autonomous drive could occur there because it is a closed set. So unlike the streets we have in the cities where a lot of cars are running all the time, it becomes very busy. In the mining set, there are very few cars, so it's easier to manage. So a lot of image identification could go on in the mining business. So meanwhile, for this paper is more on the exploration part by combining different type of data together. So it's a little bit interesting. I myself, I'm not expert on it. It's a little bit pity that Fan Huang, who is expert on this, he could not attend today because he's sick. He planned to come. It would be great if he could come in and share his perspective, because he's also working closely with the industry in Australia. So that's just some of my comment in and interpretation for it. I don't know. So any of you would like to share several of your ideas, thoughts, or questions? Or we could jump to Yang's question that why they use the black photo as the training data, or because the resolution is not high enough. That looks black for our naked eye, but if it is in really high resolution, some pixels that have brightness.
I didn't read the paper. Well, I'm actually interested in, or maybe just a related question. So what's the size of that sample they used in the training, the scale? Like, is this a like large scale, kilometer scale, or just a very small region? What's the basically what's the dimension of the image they showed in the paper?
The paper didn't give us detailed scales. But from the map, I think it may be the kilometer or meters scale.
Okay.
Because this map is from others' papers.
They took the photo like with satellite or with drone. That may be able to tell you the scale. If it's drone, I assume it won't cover a very large area. But if it's satellite image, then potentially can cover maybe tens of kilometers or even larger area.
Images from the satellite, but it didn't show in this paper.
Yeah, I think it's very likely to be a satellite. So if you look at this one, if I zoom up, so you could see that, I mean, even this drone, it must be flying really high.
Okay, I see. Yeah, so at first I thought it's just like rock samples you guys used.
No, it's not a rock. I thought it's a rock sample too, but it's not. Actually, if you look at this, if you really
something under a microscope. Okay.
Yeah, if you zoom in like that, there are some bright part in the dark paper.
Yeah.
I mean, because the one I attached was a compressed version. If you use the uncompressed version, then yeah. So they have some water.
Is no color about the point.
Yeah, there's some color. You see, there's some brightness here. Yeah, I think it's mainly because of the resolution problem. Yeah, there are.
It's not completely black. Almost.
Yeah, it's not completely black.
Maybe 99.99% of the pixels are black.
Yeah. So Ben was asking that do they combine with the drilling data? I think so, but I don't think the main point that they want to make. Here, most of it is still related to the surface process. So like the structures, the mapping that people could do, and you don't really have to drill to know the results. Because I think for something, I think they showed a cartoon early on. I like it actually. So yeah, something like this. So you look at that, then yeah, for this photo, for example, you don't need to use the drill core to know the structure, but there are some hidden part here, for example. that is not directly observable by satellite, but you have to combine with other data, other sensors that you can get. So I think this one is very practical. What the speaker that he's going to speak, I think he must have a lot of connections with industry. That it is very different than probably the rest of the papers we read in our paper reading, because a lot of those are talking about big science idea, but this one looks very practical.
So the point of this paper is to, based on all sort of sensing techniques, and then automatically identify the mineral types from either satellite image or from hypospectral image or something else.
Well, from all sensors, I think, what they mean.
Combined. Okay.
Yeah. Because they also like say have those crewed and uncrewed air flights, airborne service.
So basically, it has a potential to, well, in this paper, it probably just focus on like a mining site. So it's kind of local or regional scale maximum. But say if you have a satellite image for the continent, and at the same time, you also know the mineral compositions or whatever, like chemical compositions, like those kind of major elements of the continent. And you can apply sort of same ideas to map like continental scale chemical composition or rock composition.
I'm very dubious about that. I don't think it's in the same scale as they would like. They would be able to tell. I think this is a very exploration, economic geology related. So I think that the only could apply to places where, for example, they do have the airborne data. So with the flights, manned or unmanned flights. But I think if you look at the continental scale, then that is only a very small proportion with this type of data that is available. So unless you only rely on satellite images, which, I say I don't think you could get anywhere close to that. But maybe you are able to enter. I think for this one, it looks promising. The problem is that figure 5, we don't know the scale. If we know the scale, this one that looks a little bit promising because they were showing on figure 5. They don't tell you what type of rock they are, but they can tell you what the dust clay, which is already good enough. Feldspar vein, not too bad. Yeah, I think so. I think they're trying to combine. Yeah, I think that's the key point that they're trying to point here, is that they're trying to combine all this together.
Yeah, maybe I can add a little bit on that, but not from machine learning perspective, but from geophysics perspective. I think in mining industry, people mainly use electromagnetic method. At least in Australia, it's just a potential field measurement, because all these kind of minerals, either copper or kind of metal things, they are mostly sensitive. Mostly they are sensitive to kind of empty magnetoloric or electric imaging method. So I think if they really want to combine everything together, or they should add something like from geophysics perspective, at least from this kind of a typical applied techniques in mining industry.
Okay, but from my interpretation, that the problem is still the resolution, the scale we're talking about. So electromagnetic, I think for certain fields, so that people went down, they looking for prospect mining. Probably there were that available. For most parts, I don't think that it would be as available as this images data, either from satellites or from the onboard service. So those are covered really wide.
Yeah, it depends on the skill.
Okay. Okay, it's a sort of it's interesting. It broadened us horizon to see what the speaker is going to introduce. It look like probably going to more general talk, but it's okay. We can know a little bit beyond what we normally do. Okay, I think that's my